been almost 2 weeks ago now, we started talking about dosage calculations, and we looked at 3 ways to do dosage calculations. And the first, of course, was the formula. This is reliable and simple as long as you know what each of those pieces mean and what to go into those spots. But it had weaknesses. The biggest weakness being, of course, if you had to go through multiple conversions, it might have to be applied more than once. But also, it only applies in certain straightforward situations, only single dose applications. Second method we looked at was a proportion. Now, one of the advantages of the proportion was there's nothing to memorize. You didn't have to memorize a formula, and you just matched things up. You matched up the units, milligrams on top on one side, milligrams on top on the other side, or whatever those units were. But it had the same weakness as the formula, was that if we had to go through multiple steps, you would have to set up multiple proportions and do this over and over. Then we talked about dimensional analysis. Dimensional analysis had several strengths. One is there's nothing to memorize. No formulas, nothing like that. Two, you didn't even have to understand what the units were. The units dictate the calculation. And third, I should say, you could have as many steps as you needed. When we get into some of our IV flow rates, we might have 4 or 5 steps in that calculation process. The dimensional analysis can handle it all at once, all in one long, big step. So today we're going to look at more dosage calculation examples. I'll scroll back up. I see a couple of you writing. And we're going to look at more dosage calculation examples and look at some of the strengths of each of these, some of the strengths of dimensional analysis. I'm not going to do all the other methods. We're going to pretty much stick to dimensional analysis from here on out. But if any of you do like the other methods and want to see any of these problems I do done with one of the other methods, just speak up and tell me, and I will go back and redo that problem with one of the other methods, just so you can see how it applies. It's actually kind of nice sometimes to see the difference on which one's easier, why I pick the dimensional analysis as being the easiest method. But again, some people like having a formula where you just plug in numbers and calculate, so I can totally appreciate that as well. So the first example we're going to start off with is we're going to look at an order for 750 milligrams ibuprofen Q6H. Now the Q6H, that's part of that vocabulary that we mentioned the week before spring break. On page 150 in the textbook, if you're looking for it, it has all those abbreviations. It really doesn't affect this calculation at all. But it's just saying every 6 hours. Where that would affect your calculation would be in another few days. We're going to talk about safe dosages. If you're double checking a dose to see if it's safe, that is important to know that this is being administered every 6 hours, because many of your safe dosages are given in total amount that can be administered over a 24-hour period, or if the safe dose happens to be given in an amount per every 8 hours, we have to be able to adjust that to show what it would be for 6 hours to make sure we match up, or that we're at least within the safe range. So then let's look at our supply. Our supply might say, look at the bottle and it says 500 milligrams scored tablets. So an important word here, pair of words I should say. Tablets mean, first of all, they can be divided. If it were to say capsules, capsules cannot be split. For a capsule, it's all or none. Now, the advantage to capsules is they can be loaded with as much medication as you want because it's just a powdered medication, a granular medication inside those capsules. So you can go to your pharmacist, have the pharmacist measure them out and put the right amount or a multiple of the right amount in each capsule so that you can administer just a whole number of capsules. A tablet can be divided. And the word scored typically means it can be divided in half. We can't necessarily cut a tablet into as small a division as we want to. If it's a third of a tablet, we don't want to try to be judging where a third of a tablet is. Partly because you really can't just measure it out and take 1/3 of the length because of the rounded ends and everything. It doesn't work out to be exactly that way. So most tablets are scored, and when you're working with tablets, you do have to round to the nearest half of a tablet. So the way we're going to set this up, we start off with the doctor's orders. Doctor's order is 750 milligrams. To do the dimensional analysis, though, we're working with fractions, because that is just a simple amount. It's not a rate. We turn it into a fraction by just putting it over 1. If it were a rate, it would automatically have the fraction form in it already. Now then, the only other thing we need out of here is the conversion from the label. That's this right here, 500 milligrams scored tablets. So we're going to multiply by a conversion factor. Milligrams are on top here, so in our conversion factor, milligrams are going to go on bottom. 500 milligrams per 1 tablet. Now the milligrams cross-cancel out. 750 times 1 tablet is 750 tablets. On bottom, 1 times 500 is 500, and then we just divide it out. 750 tablets divided by 500 is 1.5, or 1.5 tablets. Now that happened to come out exactly on a half, so we don't have to round it. But if it wasn't exactly on a half, we would have to round to the nearest 1/2. When we do that, you have to be a little careful when we're looking at a number line at 0, 1, 2, or 3. We're also looking at half in each of these. So our cutoff would actually be at 0.25. Now, if you need less than a quarter of a capsule, it's probably not worth giving the medication. But between 1/2 and 1 is 0.75, 1.25, and on up. You guys get the picture. So let's say that this came out to 2.3 tablets. Well, 2.25 would be the halfway point here between 2 and 2.5. 0.3 would be here. That would round to 2.5 tablets. I'm going to cross that off because that's not part of that problem. But so you get the point. That would round to 2.5 tablets instead of 2 tablets. A little bit more awkward because we're used to seeing 2.3 rounding down, but when we're going to the nearest half, we have to adjust for that extra possibility in the middle. Okay, let's get back to another one. Let's say we have an order for 80 milligrams. Mixer, supply, vial. Whenever you see the word vial, that is implying a liquid medication. Let's say on our vial, the label is 16 milligrams in 5 milliliters. So again, this is just a conversion factor. It might often be written as 16 milligrams per 5 milliliters. It means the same thing. Either one of those is implying equivalency, saying that 16 milligrams equivalent to 5 milliliters of that fluid, of that liquid. So we can use that then as a conversion factor in our dimensional analysis. So as always, we'll start out with the doctor's order. In this case, 80 milligrams. Now, once again, that's just an amount. There's no rate there, so we have to make it into a fraction by putting it over 1. Now we'll bring in the, we should say what I want to administer. In the previous problem, when it was tablets, it's obvious how we're going to administer. Since this is a liquid medication, it's going to be administered with a syringe, which means we need to know how many milliliters administered to the patient. So to get to that, we will use this information on the vial. Milligrams on top in our original doctor's order, so we have to put milligrams on bottom here. So 16 milligrams in 5 milliliters. Milligrams are going to cancel out. Now all we have left is milliliters, and that is the units we want, so we're ready to go ahead and calculate this out. 80 times 5 milliliters is 400 milliliters. Over 1 times 16 is 16. Then if we divide that out, 400 milliliters divided by 16 is 25 milliliters. So we would administer 25 milliliters of that medication to that patient. Well, those are relatively simple examples. Let's make it a little bit more intensive. So let's say our order is for Axid 0.15 grams, POBID. So again, the POBID doesn't mean a whole lot to us right now for the calculation. BID typically needs as needed. PO means orally or by mouth. What we're more concerned about is how much you're going to administer in each individual dose. So we're going to look at the supply. Our supply here is a bottle or a vial. Not a vial, it's a bottle containing 60 capsules. For Axid, and it is 150 milligram capsules. So when we look at this, often, and this is one of the things that's going to be the toughest part in most most realistic medical applications, is there tends to be more information than what we need. If you look at the label of any bottle of medication, you see stuff that really doesn't play into the dosage. Here, 60 capsules. We don't care how many capsules are in the bottle. We care what each capsule represents. We'll start out with the doctor's order again. 0.15 grams. Again, this is not as a rate, so we'll make it into a fraction by putting it over 1. Now our equivalencies here, 150 milligrams, or 150 milligram capsules is saying 150 milligrams equivalent to one capsule. Now, unfortunately, the unit we have here is not milligrams or capsules, so we're missing something in there. Fortunately, this is grams to milligrams is a standard conversion. I'll put grams on bottom, milligrams on top. We know that 1 gram is 1,000 milligrams. So the grams will disappear. Then in our next step, we'll go from those milligrams to capsules. So 150 milligrams goes on bottom because milligrams were on top. Capsule goes on. So now we'll cancel out the milligrams, and what we have, our only unit is capsules, which is the unit that would make sense to administer here. So on top, we got 0.15 times 1,000 is 150 capsules. On bottom, 1 times 1 times 150 is 150. Well, 150 capsules divided by 150 is, of course, just 1 capsule. Our next order for oxal, 0.375 grams, POQ8H. So again, the POQ8H doesn't affect us here right now. PO is just by mouth or orally. Q8H is every 8 hours. Again, if we were looking at safe dosage, to figure out a safe dosage, that Q8H would be important to us to be able to compare that to however many hours the doctor recommends or what the label recommends. But for right now, we're just calculating a single dose, so that doesn't mean supply. 50 milliliter bottle, labeled constitute oxal oral suspension, 125 milligrams milliliters. There are a few things going on here. First, unneeded information. We don't care how big the bottle is, other than, well, we might need an extra bottle, if more than one bottle, if it this or more than what's in there. Next part, reconstitute oral suspension. So reconstitute, generally when we have most of these medications, we mentioned this last time around before spring break. Often these medications are shipped in a sterilized vial, but it's not a liquid medication, it's just powder inside the vial. And you reconstitute it when it comes to you by adding sterile water to it. Excuse me. Mainly because shipping costs. Most shipping costs go by weight. Liquid water is heavy as far as shipping is concerned. So if you can just ship the powdered medication and add the water on site, you save a lot of those shipping costs. Typically, they will say how much water to add to the vial. This one, I didn't put that in there. But all that means is you're going to add a specified amount of sterile water or normal saline into that vial to mix it. Oral suspension, the term suspension, it means it must be shaken before you. If it said solution, you don't necessarily have to shake it. In fact, a solution is actually better if you don't shake it. A suspension, it has to be shaken, and then if you're putting it in a vial, you load the vial right away. A solution, if you do end up shaking it by accident, you actually have to let it sit and settle for a minute before you load. Because a solution, shaking it can actually cause the medication to slightly fall out of solution. Whereas a suspension, it has to be shaken to get the medication evenly spread throughout the liquid that is being suspended in. And of course, the 125 milligrams in 6 milliliters, that once again is an equivalency telling us 125 milligrams equivalent to 6 milliliters. And since this is a liquid, we are trying to find how many milliliters of this medication we're going to administer to the patient. So once again, we start out with the doctor's order. And the doctor's order is 0.375 grams. Again, there's no rate given there, so we can just leave it at that. Put it over 1. Once again, this is in grams. Our equivalency is given in milligrams, so we have to make that transition. So 1 gram is 1,000 milligrams. Grams will cancel out. We're now in milligrams, but we still need to get to milliliters. Milligrams are on top, so we're going to put milligrams on bottom. And our equivalency here, 125 milligrams in 6 milliliters. So now the milligrams have canceled out. Our only units left is milliliters, which is what we want for administering a liquid medication. So on top here, we got 0.375 times 1,000, that's 375, times 6. It's going to be, of course, 2,250. 1,250 milliliters over 1 times 1 times 125. That's going to be 18, but let me just, 2250 divided by 125 is 18 milliliters. So that is the amount that we need to administer to our patient. Now here's the only place we would need this number here. This is 80 milliliter bottle. This being 18 milliliters means there's going to be more than enough in a full bottle to fill our syringe, so we don't have to worry about that. Do we have any questions on these so far? So next, we're going to have an order. Codeine. PRSS. POQ4H. PRN pain. So this order, again, has some interpretation to do. PO is still by mouth. Q4H, PRN. The Q4H means up to every 4 hours. The PRN means as needed. So that means they can give it to you every 4 hours, but they don't have to give it to you. They can wait longer if they want to. Just no more often than every 4 hours. And then for pain, it is for treatment of pain. PRSS, GR, of course, is grains, and SS is our Roman numeral for 1/2. So this is 1/2 a grain, is what that is telling us to administer. Then our supply. Our supply here, we have actually 2 options. Option 1, we have 15 milligram tablets. Option 2, we have 60 milligram tablets. Why would we worry? Why would we have more than one option? Well, 1, we don't want to divide tablets if we can avoid it. But we also don't want the patient to have to be swallowing like 8 tablets if they can just swallow 2. So once again, we'll start out with the doctor's order here, which is the 1/2 grain. Put that over 1. Our first step here is going to have to be to get rid of the grain. Grain is on top, so we're going to put grain on bottom. And we have an equivalency telling us that 1 grain is approximately 60 milligrams. Now, I know I mentioned this back at the end of Unit 2 when we were doing these equivalencies. 1 grain is not exactly 60 milligrams. It's actually like 62.7 milligrams. But when we absorbed it into the metric system, because it was actually part of the empirical system, the old system, when they absorbed grains into the metric system, they rounded that number to 60 milligrams per grain just to make it easier to work with. Just like 15 grains in a gram is also not accurate. It's closer to 16, but they rounded that off to make it work easier in the metric system. So anyway, the grains will cancel out here. We would now be in milligrams, so we can convert into our tablets. Now what I'm going to do here is I'm actually going to complete this part of the calculation first. 1/2 times 60 milligrams is 30 milligrams. 1 times 1 is 1. What the doctor's order is really asking for is just 30 milligrams of codeine. Looking at my options up here, the 60 milligram tablets are too big. I would be literally administering 30 milligrams over 1 times 60 milligram tablets for 1 tablet. If I calculate that out, I get 30 tablets over 60. Milligrams cancel out. Or 1/2 of a tablet. Now again, we can do that. We're allowed to cut tablets in half. But we try to avoid it because, one, it's messy and it can be not a terribly precise process. But if we looked up the other option, order for 30 milligrams and 15 milligram tablets, milligrams cancel out. 30 times 1 tablet is 30 tablets. 1 times 15 is 15. 30 tablets divided by 15 would be 2 tablets. Much neater to give 2 tablets to the patient than to try to give a 1/2 a tablet. Either one of those would be accurate. That would probably be the preferred method, is to use the 2. Let's take an order for Floyd. 125 milligrams PO daily. Excuse me. Our supply. We have a bottle for tablets. $50 microgram tablets. So that symbol here, microgram, you might be more familiar with it like this. 1,000 micrograms in a milligram. I'm going to give you guys about a minute. I want you to do that one in your notes, and then we'll go over it together. once again, we'll start with our order of 0.125 milligrams. Put it over 1 to make it a fraction. Now here, we need to get to micrograms. So put milligrams on bottom to get rid of it. 1 milligram is actually 1,000 micrograms. A milligram is 1,000th of a gram. A microgram is a millionth of a gram. So it works out to 1,000 micrograms in a milligram. The milligrams are gone. Next, for the milligrams, we have micrograms. We have 50 micrograms per tablet. Micrograms cancel out. On top, 0.125 times 1,000 times 1 tablet is 125 tablets. On bottom, 1 times 1 times 50 is 50. And 125 tablets divided by 50 is 2.5 tablets. One of the advantages that I pushed about using dimensional analysis over some of our other methods is that we don't need to know the unit. We don't need to be familiar with the units that we're using. It would help if we did, but we can run into a situation like this one. We might have an order for potassium chloride, 40 MEq BID. So the BID just means as needed again. PO is orally. MEq is something called milliequivalents. A milliequivalent is not necessarily a standardized unit. It is often different for each medication. But fortunately, we don't really need to know what it is. We can just follow the information on the label. Let's say the label on our supply says vial of 15 milliliters of oral solution. It is 20 milliequivalents milliliters. So what this is saying is that the whole bottle, I should put the 15 milliliters in parentheses, the whole bottle is 20 milliequivalents of medication. Bottle is 15 milliliters. That tells us that we have that equivalency of 20 milliequivalents equals 15. Excuse me. So again, we'll start out with the doctor's orders. I'm going to stop writing the word order up here, but you know what I mean. We're starting with doctor's orders of 40 milliequivalents. Put that over 1. And our conversion here, 20 milliequivalents would go on bottom. 15 milliliters would go on top. Milliequivalents cancel out, and on top we have 40 times 15 milliliters is 600 milliliters. Over 1 times 20 is 20. We divide that out, that is simply 30 milliliters. Now, 15 milliliter bottle, which means we have to use 2 vials here to get that amount of medication into the patient. Another unit we might not be familiar with, something that's used for antibiotics, amoxicillin, penicillin, and such all the time. Let's say our order is for penicillin. $1,200,000 units. IM. The IM simply stands for intramuscularly, so it's just going to be an injection into the muscle. Supply. Label on our supply is 100,000 units, 5 milligrams, and 15 milligrams and 4 milliliters. I have a couple of cycles of this conversion. If we were using the formula or the proportion, we'd have to repeat this calculation a couple times. But with the dimensional analysis, we just do it once. We start out again with the doctor's orders. 1,200,000 units. Just put it over 1. Now we're getting rid of units, so I'm going to put units on bottom here. We have an equivalency of 100,000 units per 5 milligrams. So now the units have canceled out. We're in milligrams. Well, we need to get to, this is intramuscular, it's an injection. Injection, of course, is going to be measured as fluid as milliliters. We need to get rid of milligrams, so I'll put them on bottom. We have 15 milligrams. 4 milliliters. Now the milligrams cancel out. The only units we have left is milliliters, and that's what we want. Now we can calculate this out. Now because the large amount of zeros here, I am going to do a little bit of cross canceling. Typically, I only recommend you cross cancel zeros. The rest we can divide out later. But I'm going to cancel. I've got 1, 2, 3, 4, 5 zeros here and 5 zeros here that I'm going to cancel out. So I'm dividing each of them by 100,000. So now this is 12 times 5 would be 60 times 4 milliliters is 240 milliliters. Down here, this is 1 times 1 times 15, which is 15. 250 or 240 milliliters divided by 15 is 16 milliliters. That would be 16 milliliters administered to the patient. You can see there have been 2 units here. One is just units, and the other was milliequivalents that we might not be familiar with, that we might not know what they mean or what they represent. But they're defined on the label of the medication, and that's all we need if we're using dimensional analysis to convert that into something that we can actually administer to our patient. Let's say we have an order for astropine sulfate. PR 1/300th. Our supply, astropine sulfate. Milligrams in 5 milliliters. So first, the word solution tells us you don't have to shake it. Or if you do shake it, you should let it sit and calm for a minute before you load a syringe. Start out with that order of 1/300th of a grain. Put it over 1. Need to convert that into something a little more useful, so to get rid of grains, I put grains on bottom. 1 grain is 60 milligrams. So the grains are gone. Still need to get it to a liquid, so I need to get to milliliters. Milligrams on bottom, and this says 2 milligrams and 5 milliliters. Now, depending on the label, some of the labels may have just listed that as 0.4 milligrams per milliliter. That would, when you see it listed like that, you still have to be able to say any rate can be a equivalency as 0.4 milligrams would be equivalent to 1 milliliter. That would be the exact same rate as what we have here. Anyway, we're going to cancel out the gram or milligrams, and now we have milliliters as our only unit, which is what we want. So 1/300th times 60 times 5 milliliters is actually 1 milliliter. Over 1 times 1 times 2 is 2. That is 0.5 milliliters. So that's all you would administer to that patient is half a milliliter or 0.5 milliliters. There are a couple of things I want to mention here. One is talked about reconstituting a solution. And we mentioned that often those medications are we call it dry shipping, where it's just a powder in a sterile vial and you have to add saline or sterile water to it to reconstitute it. Typically, there's going to be instructions on the bottle. For example, you might have a label that says vial contains 600 milligrams of medication, whatever the medication is. It might say concentrated heparin or concentrated whatever. And the instructions were reconstitute with 4.6 milliliters sterile water. So the sterile water, again, just saline or sterilized water, to 120 milligrams per milliliter. So all this is telling you is add 4.6 milliliters of sterile water to this vial. Once it is mixed, it will have a concentration of 120 milligrams per milliliter. Total volume is actually going to end up being 5 milliliters. Because you have the powder mixing in with the water, it will slightly increase the volume of the total solution. Well, it doesn't say whether this will be a solution or a suspension in this instruction, but the total volume will be 5 milliliters. We know that because 600 milligrams of medication at 120 milligrams per milliliter, 600 divided by 120 would require 5 milliliters to contain that medication. So next time we will start talking about IV flow rates. IV flow rates are where the dimensional analysis really starts to shine, because IV flow rates can be taken through several steps of this calculation, where the formula or the proportion might have to be applied 3 or 4 times or more to get to the end of the calculation. Where dimensional analysis can only be done once, we split it into one big chain and we have it all done. For right now, there is page 172 through 173, 1 through 9, the odds. That's actually about reconstituting solutions. And a little bit of review if you want to go back to our homework from last time on the dosage calculations. But I'm going to trust you guys have those done. So you guys have a great day. Hopefully we'll see you all on Wednesday to talk about IV flow rates.